We're going to talk about the disk washer method and volumes of revolution. Let me just briefly explain what a volume of revolution is. We talked in the volume by slicing video about how you have to have some way of defining what the cross-sectional area is in terms of one of the variables. Volume of revolution is just another way of doing that, but it gives a specific type of solid. So if let's suppose I have this curve here, this is how I draw every generic calculus curve like that, where, okay, so that's y equals f of x. And let's say that I want to form a solid by doing this. I want to revolve that curve around the x-axis. So let's imagine that there's three-dimensional space here going back into the page. And what I do is I take this curve and I revolve it around the x-axis. So one cross-section ends up being that circle. And over here, actually let me just use a different color to make it stand out. So one cross-section ends up being a circle, and over here the cross-section ends up being a bigger circle. The point is that we can take this circle, let's just shade this in, and I'll draw it out here so you can see what we're doing. So this dot right here in the middle, if you imagine, I've taken the circle and I've now flattened it out on the page. That dot is actually the x-axis just running right through the middle of that circle. I know it's kind of hard to draw here. Let me just do it again so you can see. So that's the dotted line is behind the x-axis, and this blue dot goes right through the middle. Now, take a look at what the radius of this circle is. We know that this point up here is just going to be x f of x, just like every point on a function. So what that means is that since the height over the x-axis is f of x, that means the radius is just equal to f of x. So I can put in that radius here. And that means that if the radius is f of x, then the area of this cross-sectional circle is pi times f of x squared. So that's how you get the cross-sectional area of a volume of revolution. The defining feature of a volume of revolution is that we take some curve and revolve it around another line, and that just gives us a very convenient way to define the area, because we know that we're getting circles as cross sections, and there's always a very specific way that you can find the radius of that circle. I really can't do any better than this animation to show you what's going on. So take a look at this curve. This is the curve y equals the square root of x. Now, watch what happens as we revolve the curve around the x-axis. See how we form this bowl-like solid, and where every cross-section is just going to be a circle. Now watch what we do to form a single cross-section. What we're going to do is we're going to choose a particular point x along the x-axis. And notice how we get a circular cross-section, but we can give it a little bit of thickness dx in the x direction, just like we did with the slices in the previous video. Now, as far as the radius goes, since this point that is just going to be x f of x, the point that's on the surface of the solid is just x f of x, that means that the radius is simply going to be y, or or square root of x. That's the radius of the circle. Okay, let's do an actual example. What I want to do is find the volume of the solid that's obtained by revolving the curve y equals x plus 1 around the x-axis. We usually say revolving about the x-axis on the intervals 0 to 1. And by the way, sometimes you'll see this described as revolving the curve around an axis, and sometimes you'll see it as described as revolving a region of area around the x-axis. It doesn't really matter. We're talking about the same solid either way. So revolving, I didn't mean to do that one. So we're revolving this curve around the x-axis, thereby forming cross sections that look like this. So the radius of each of these circles in terms of x is going to be x plus 1, right? Because this point here, assuming that this is x, this point is going to be x plus 1. So its y value is x plus 1. That's its vertical distance from the x-axis. So let's set up the calculation. First of all, the radius, this is a little bigger, the radius is equal to x plus 1, and therefore the area of one cross section is equal to pi r squared, which is pi times x plus 1 squared. So we now know the area of one cross-section. Let's make it a slab, though. I'm giving it a little bit of thickness that we know that we call dx. So the volume of one slab is equal to pi x plus 1 squared dx. So let's just quickly write the statement of the problem that we're trying to solve. We'll zip through that. So that's the formal definition of the solid. So let's write out the integral. We know what the volume of one slab is. So the volume of the full solid is going to equal the sum of all the slabs. Let me bring this in a little bit so you can see it, which we get through integration. We're going to integrate from 0 to 1. Where did I get the 1 from? Because we're finding the volume of the solid on the interval 0, 1. And we just integrate the cross-sectional area. Pi x plus 1 squared dx, which you can think of as either I'm integrating the area function or I'm adding up the volume of all the slabs. Either way, you can see either of those in that expression. So this just gives us a volume. I'm just going to zip through the algebra. So that's the volume of this solid, 7 pi over 3. So let's have you do one of these just so that you know how to do this. So let's write the same problem we were doing before with the video. We'll put up the function y equals the square root of x, and let me write out the interval 0 to 2. So I'm going to do this, and I'll write it out. And just so you know, I usually use this sort of circular arrow to indicate that we're revolving the region about a particular axis. So here's the region that's being revolved. There's the curve, and I'll put the question up.